One thing that differentiates robots from other machines is that they are able to move themselves or other things around. In other words, they really change the environment they live in. In this video, I will show what is needed for a robot to move from A to B. Although this might sound easy, it is still quite hard and uses a lot of compute power. Humans usually try to make a mental model of the environment, and we mostly use our eyes in order to get from one location to the other. But we also use a lot of knowledge about the environment. Do I think this bridge will hold me? Or do I know the door is locked? Doing this just based on knowledge and visual information is still way too complex for a robot. So the robot uses other sensors to localize and plan its way. One of the easiest ways of knowing where you are is to use wheel encoders. These are sensors that count the rotations of the wheels. In that case, you can calculate the distance the wheel has traveled. By using the encoders of all wheels, you can know the position of the robot relative to its starting point. You can imagine that this is computationally easy, but has some limitations. Depending on the surface of the ground, the wheel might have slipped, creating errors. And to make it even worse, these errors will accumulate over time. In this example, I use a mobile robot, but robotic manipulators, of course, also use encoders in their motors to know what the state of their motor is. Estimating the change of position over time by using motion sensors is called odometry. Apart from wheel encoders, we could also calculate this location based on images from a camera, which is called visual odometry. But you could also use IMUs or sensors. Odometry is a dead reckoning strategy to know where you are. It therefore still has a problem when you pick up the robot and put it somewhere else, also called the kidnapping problem. Let's have a look at another way for the robot of localizing where it is. The first thing you will probably think of when you want to know where you are is GPS. But it's only accurate to around 10 meters. But more importantly, it does not work indoors. Indoor localization is therefore really hard. Sometimes you can change the environment to make it a bit easier for the robot. You could try to mimic a GPS-like system with beacons, but that's usually still hard due to reflections of the signal. You could also enrich the environment with QR-like markers, which are easy for the robot to spot. But in a lot of situations, you are not supposed to change the environment at all. So the robot needs to localize itself. A common way to solve this is to use a LiDAR. Imagine the robot already has a map of the environment and it needs to locate itself in this map. One way of doing this is called Monte Carlo localization. This algorithm will generate a large number of random points in the map. It will then, for each point, calculate the expected LiDAR data if it were at that point. It can then compare this with the actual sensor data and find the spots which are probable locations for the robot. Depending on the complexity of the map, this might already generate a cluster of possible points, but it could also generate multiple clusters. By driving around, the robot gathers more and more data, and the robot will more and more be able to know where it is. You can imagine that this is computationally hard. The more random points you put in the map, the longer the computation takes. The previous examples gave an idea of localization of a mobile robot in an indoor setting. But also manipulator robots need to know where their end effector is. The space is more limited though, and it helps that all the motors are connected, called the kinematic chain. By knowing the orientation of the motors, you can calculate the position of the end effector. This is called forward kinematics, from joint angles to Cartesian space. With this, localization of the end effector becomes relatively easy. But sometimes the robot does not have a map of the environment. In those cases, it needs to create the map itself. This looks like some sort of chicken-egg problem. In order to create the map, you need to know where you are. And in order to know where you are, you need a map. The robot needs an algorithm to simultaneously localize and map the environment, also called SLAM. There are multiple implementations of SLAM algorithms, for example using Kalman or particle filters. One metric of how good the algorithm creates this map is loop closure. When the robot is driving around the building and gets back to its starting point, the SLAM algorithm needs to close this map. For SLAM algorithms to work, you need a feature-rich environment. Worst environment for a robot is a long corridor without doors. How will it, based on, for example, LiDAR data, determine where it is? A lot of SLAM implementations use LiDARs as sensors, but you could also use other sensors. Cameras, sometimes combined with markers, can also be used. But you could even do SLAM on the signal strength of multiple Wi-Fi routers located in a building. As long as a unique point in space has a unique sensor input, your SLAM algorithm could work. As humans, we know that most walls are static, but animals or cars can move. Based on just the sensor data, the robot needs to decide if the walls are moving or whether the robot itself is moving. This is why you also need odometry in some way. Now that we discussed some ways for the robot to create a map and know where it is, we can finally try to plan how to get from A to B. Of course, it's one thing for the robot to know where it is, but usually a robot, the end effector of a robot arm, needs to go to a place or position. For this, we need path planning or motion planning algorithms. For mobile robots, this means it needs to have a map, its own location, and a position to go to. There are multiple algorithms a robot could use: Dijkstra, A*, D*, just to name a few. This type of planning is called global planning and expects a static environment. But usually you have a dynamic environment. And only when a robot senses its environment, it knows there might be some dynamic objects nearby. It then needs to recalculate its path, which is called a local planner. Taking the global and local planner into account, the robot can calculate how to move. Getting from this desired direction to motor commands is called inverse kinematics. This holds for both mobile robots and manipulators. Manipulators usually do not need to plan within a map, but do need to plan how to get from A to B as well. For this, they also need to do inverse kinematics. Especially for manipulator arms, this can become quite complex. You need to calculate the desired motor location from the location of the end effectors. The more motors you have in this kinetic chain, the more dimensions you add to your research space. This holds for both mobile robots and manipulators. Manipulators usually do not need to plan within a map, but do need to plan how to get from A to B as well. For this, they also need to do inverse kinematics. Especially for manipulator arms, this can become quite complex. You need to calculate the desired motor location from the location of the end effector. The more motors you have in this kinetic chain, the more dimensions you add to your search space. But there might also be multiple possible solutions for one location. Again, like mobile robots, robot arms also need to plan their path. This is done using inverse kinematics, from Cartesian space to joint angles. The robot needs to plan a path from A to B, within the limits of the angles. Most of the time, this is a trade-off between deterministic solutions and speed. Some fast planners might come up with a different solution each time you plan. But we also need to solve the inverse kinematics of the arm. Where the forward kinematics only has one solution, inverse kinematics might have multiple. You need to get the orientation of all angles from one point. You therefore need a kinematic solver to solve this for you. And like with mobile robots, it also makes sense to take the environment into account, making sure not to bump into things. These constraints also need to be fed to your solvers. With this presentation, I hope I gave a bit of an understanding of why it is hard for a robot, mobile or manipulator, to get from A to B. It involves localization, mapping and path planning. all computationally heavy algorithms.